and my dissertation was to design an audio synchronization device for visually impaired rowers. My dissertation was designed so that visually impaired athletes who train in rowing can train together on the land. So there's already methods in place for them to be able to train together on the water, but there isn't anything in place for them to be able to train on the land. And in winter, most training is done on the land. So essentially we decided to get a load of visually impaired athletes together, read in their positions on the rowing machine, and sonify using audio signals that allow them to get back in time with each other or speed up or slow down. For the outcome of my research, essentially there's a lot of devices out there that are helping visually impaired people move around from A to B. And there's also a lot of devices that help visually impaired people in sport. But there's not that many for rowing. There's none for rowing really. I mean, there's one device that allows visually impaired people to train together in a boat. So we thought we'd tackle that area head on really, and try and develop a visually assistive device for rowing on land. While doing the research, it became clear that audio was the clearest way to supply assistive technologies for visually impaired people, but it's very important on how you use the audio. So onomatopoeic sounds, so sounds that describe a movement, transfer a lot better than just a normal sound, so you had to develop a proper sound that's designed to signify the information you want and not just a sound that's like, get in time with this. So it became clear that the sound design was going to be quite important during the development of the process. Other parts of the research pointed out that you can just make noises and get people to come in time with each other. But if you make the right noises, people will be more inclined to get in time with each other than if they had just a beep, 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 beep sort of thing. To develop my dissertation, first of all we had to decide on how we're going to read in where the athletes are on the rowing machine. So we had to decide on a sensor technology. So we had to find an appropriate sensor so we could track where they were on the sea at any point. We tried accelerometers, gyroscopes, potentiometers, but in the end it was easiest to use an infrared sensor. The infrared sensor didn't get in the way, wasn't hard to mount, was small, was light, was cheap, and it worked exactly the same every time. It didn't require any configuration. Once that was developed, it was just a matter of getting that information into the computer. So I went with Arduino for that, which was a technology I hadn't used before, but was ended up being really, really useful and really powerful. So you could take the information from the infrared sensors straight through the Arduino and into Max 7. So using Max 7, we're able to develop quite powerful software with modules, and you don't need to code it all from scratch. And yeah, so it was just a matter of making sure that the software was scalable, because there needs to be able to train just 2 of them, or 3 of them, or 4 of them, or 8 of them, or 12 of them. So the software needed to be able to accommodate more people should you want to add them in. So the Arduino was perfect for that, because you can use lots of the inputs on there. You can even daisy chain them if you need to. So once that was developed, it was just a matter of, in Max, doing some sound design, developing the curves, or the beeps, or the signals. And once they were all developed, it was just a matter of testing it, really. So testing happened in 2 phases. All the testing was carried out on simulated visually impaired athletes. This was because once a visually sighted person has the blindfold on, there isn't that much difference between a visually impaired and a fully sighted person. I went through this in my lit review in quite a lot of detail. So we used simulated visually impaired athletes, and we did 2 sets of tests. One was with experienced rowers, so they were from the rowing team from the university, and the second was inexperienced rowers, so they'd never done any rowing before. The first set of tests happened with the experienced rowers, so that we could just work on setting the device up. So their movements were perfect and everything, not perfect, the movements were better. So we just worked on setting up the device, seeing if it worked, calibration, etc., setting the waypoints. And then the second tests were with people who had no rowing experience, so probably closer to what the device is designed for. And these tests were longer, and we asked each person to row for 5 minutes, and then have a 10-minute rest, and then 5 minutes, and a 10-minute rest. We did that quite a lot of times, just so they got used to the device, and it wasn't kind of, because it's quite a different experience with this device. You have it's not normal. So once you got used to it, it became much more useful than if it was kind of jarring at first. So you need to make sure that part of the testing was foregone. So, well, the final outcome of the project was really positive. It was very clear that the device did improve synchronicity between athletes if they had it on or if they had it off. The main difference wasn't how close they got together, it was just the distance, or the furthest distance apart was a lot shorter, so they were just much closer together in general, in terms of getting to the front of the stroke and to the back. The feedback was very positive. People really enjoyed using the device after they got used to it. At the beginning it was quite alien, quite hard to use, because it's just a weird sound. You have to kind of learn it. It's the same with a lot of assistive technologies. It takes a long time to get used to them for them to be actually useful. But after 5-10 minutes with the device, it did become useful. It kind of almost sinks into the back of your mind, which is what we were looking for at the beginning. But you are paying attention to it all the time. Feedback about the sounds was really good as well. We had 2 sets of feedback, so you had waypoints, so it was certain points down the slide would signify a sound or a progressive sound, and people actually preferred it when both of them were on at the same time. The curve, the sound of the curve as it went up and down, spent quite a lot of time tweaking that, and that became non-jarring, because that was the issue, was that this device could become really annoying if you used it for too long. So it actually changed over time, so every time you did a stroke it changed ever so slightly and morphed. So if you used it for 10 minutes it would be a completely different sound from when you started to the end. There were a few issues with it. The first being that the more ergs you put in a room, the more rowing machines you put in a room, the louder the natural sound is. So it's quite hard to sonify the sound to every single person in that situation. But if we were to take it any further, you'd probably develop it so that each athlete had their own individual sound feedback. At the moment, it's using a global set of speakers. So if it was taken further, you'd want kind of headphones or everyone to have their own speaker. But yeah, no, apart from that, all of the feedback was really good. No one said it didn't work. There's definitely things I'd like to change in it, but it worked really well. I'm very happy. My favourite part about the dissertation was probably doing the hardware programming, something that I've never done before, and it probably gives me much more of an understanding of how things, or everything we have around us is designed and made, microchips, etc. And programming in general has become one of my favoured parts of the course. The dissertation was a lot of fun in general. It allowed me to combine one of my real loves of rowing with technology, and our course allowed us to be able to put them together to make something that's actually useful.